In this session, I'm going to talk about deflection of beams. It means that the beam under loading deform, and this deformation must be calculated in design. The governing actually stress in the beam is not actually only the bending stress. We must consider many things. Horizontal shear stress is another one. Deflected shape of the beam is another consideration. And we must consider many things else in order to design a beam to carry loads. Okay, we have some definition here before we reach to the calculations of deflections. There are many ways to calculate deflection of the beam, and one of them that we must discuss it is here is moment area method. But before that, we need to know about two theorems. First theorem and second theorem is here for calculations of deflection of beams. Let's consider a simply supported beam, one roller, one pin, and also a point load applied to the beam, for example, here. Under load, beam deflects, and the shape of deflections, I make it exaggerated to have a space, that's a load P, and if I go point A, point B, point C, B change its place and come to B prime. A and C doesn't change because they are on the supports. Okay, BB prime is called deflection. Then BB prime is called deflection of point B. And is shown by Greek letter delta. There are many ways to calculate this amount of delta. For example, here, because it is the middle, it's shown that deflections happen here is maximum, but you are able to calculate it at any other point. That's D and D prime. For here, E and E prime. But because in engineering, we consider the worst case scenario, we always interested and focus on the maximum bending moment, maximum deflection, maximum bending stress, maximum horizontal shear stress. These are the governing actually parameters. Then, sometimes in design we are interested in the deflection of a specific point. That's another story. But we are able to calculate them as well. There is another term that I wanted to explain here before going for deflections is deviations. Deviations means actually depart from a reference point. The two theorems that I talk about them, the name is about this deviations and slope. What is the slope of the beam at any point? If you consider point A and I draw a tangent at A, this means there is an angle between the straight line original position or configuration of the beam and the tangent after deflected shape, after deflection, we call it theta. This theta is called rotation of beam at A, or slope of the deflected shape or curve at this point. And if I draw a tangent at B, this tangent, due to loading actually, not always tangent in the middle of the beam is horizontal line. No, it's a special case of the loading make it horizontal. That tangent is horizontal, and a slope here for rotation at point B for the beam is 0. Then this angle is the difference between the two tangent line, which we called it, for example, delta theta, change in the rotations. For example, here is theta A, and we have a theta B, and delta theta is the change in the rotation between, or the slope between point A and B, which is called, for example, the theta B minus theta A. The first theory says that you can calculate this change in the slope of the tangent line to the deflection beam, and you can find out how much the beam is rotated at A if you know the rotation at B is 0. Okay? For example, if I consider D and draw a tangent line at D, then this angle is delta between theta D and theta A. You can find this as well. Always we consider slope between 2 points. Slope between 2 points. Or change in rotation of the beam between 2 points. And we calculate that. How much is this rotation? The first theorem says you draw the bending moment diagram. The bending moment diagram is, for this beam, this one. Point A, point B, and the first theory says that the area under bending moment diagram, it is shown, can be proved later in another video. I proved that the area between these 2 points of the beam is equal to, divided by EI actually. If I divide this diagram by EI, the area between A and B divided by EI is equal to theta difference between theta of A and B. That's the first theorem. Second theorem is about if I take the moment of this area with respect at any point, for example, with respect to B, it can give me the deviation of point B at the B. What is deviations called here? This is why we need the definition of deviation. If I draw the tangent at A, I continue that. Deviations is this distance of deflected point B on the deflected shape till this tangent, this length is called deviation of point B of the beam. And we called it with T of B with respect to A. We called it deviation of B with respect to A and show it TBA. If you take moment of this area, there is a centroid here. Take moment with what? Respect to B, this distance. This area times this distance is equal to, divided by EI, is equal to amount of these deviations. Okay? We called it B double prime. Then B prime, B double prime is equal to the first moment of the area divided by EI between these 2 points. Between A and B. This first moment of the area between A and B with respect to B, the point that you are looking for its deviations, divide by EI, modulus of elasticity times second moment of area of the cross section of the beam, EI. It gives you this amount. Then, what's the relation between this amount and deflection at B? Deflection at B is how much? It's this much. That's the deflection at B. How we can calculate that? We have to do some geometric work here. Geometry. I continue tangent at A, and I draw deviation of point C. Because C has no deflected, the C and C prime are consigned on C, and here I can call this C double prime. This is deviation of C with respect to A, according to the definition of deviations. Geometry says what? Geometry says that this triangle, ABB double prime, this triangle is similar to triangle ACC double prime. Write the ratio of similarity. It means that AB from a small triangle divided by AC from larger triangle, similar sides, is equal to BB double prime divided by CC double prime. What is BB double prime? Is deflection plus TBA. And what is this one? TCA. Then, I know this ratio. I know where is the location of B. Here, for example, is in the middle. Then AB over AC is 1 over 2. Is equal to delta plus TBA divided by TCA. It means what? It means that delta of B, the deflection of B, is equal to half of TCA minus TBA. I rearrange this part. Then I calculate it. deflection at B by using the second theorem, deviations. This is why we have to use and calculate deviation first and use geometry to find out deflection. For simply supported beam, you need that. What if I wanted to calculate deflection at D or deflection at E? No difference. The only thing that is different is this ratio. For example, AE divided by AC maybe is 1/3 or 1/4 of the length is equal to this delta D, delta E plus TEA, deviation here, which is the first moment of area between A and E, with respect to E is here. This area, take moment with respect to E. Then if I find out this triangle area, multiply by this distance, which is 1/3 of the base, that's the area, first moment of the area, divide by EI is equal to what? These deviations here that I show you with red color. TEA. We called it what? TEA. T, deviations of E with respect to A. Or for D, the same story, no difference. That's the deviation for simply supported beam. What happens if we have a cantilever? Cantilever beam is actually very easier. Why? Because deviation and deflection are the same. There is no need to use geometry. No need to use geometry. Let's say consider a simple example. Change this base as support as a fixed support. Use this shape, load at the free end. If deflected, we use to show the beam as a straight line. And deflected shape is like that under the load P. Then this is the original configuration of the beam. Yes. This is the tangent to the deflected shape of the beam. Yes. Then original shape of cantilever beam and tangent at the base to the deflected shape of the beam are the same. It's made very easy, the problem very easy. How? Any point that I have here, for example, point B, point C, point D, point E, the end of the beam, then this is deflection of B, BB prime. CC prime is deflection at C. DD prime is deflection at D. EE prime is deflection at D. How we show them? These are BB prime is delta B. CC prime is delta C. The rest. What about deviation of this point? Deviation means the distance from a tangent as a reference. How much B prime is departed from the tangent of the beam? Is this amount? Then TB with respect to a tangent at A, point B on the deflected shape means B prime, is equal to BB prime. BB prime. BB prime, you see BB prime already is delta B, deflection of B. This is why we do not need geometry here. If you calculate deviations, use the second theorem. First moment area under moment diagram between 2 points, divide by EI, modulus of elasticity times second moment of area of the cross sections, gives you deviations. And this deviations is equal to deflection at that point for cantilever beam. Okay? The story here for the slope is the same as no difference. Just the area between 2 points gives you the difference between the rotations at beam between that 2 points. No difference. That the area over EI in the moment diagram. Then it is better after you draw moment diagram, you divided it by EI and draw another curve. Because EI is very large number, then M over EI became very small. And it is actually, if you draw in real scale, calculations is very difficult. This is why we don't change the shape of the diagram, but we only write the real value over there. Assume that if the P is 10 kilonewton and the span of the beam is 3 meters, what is the shape of the moment diagram? Let's say I use it because I have the diagram here. Let's say I use the same simply supported beam. This is 10. This is 1.5 meter, 1.5 meter kilonewton, and M is equal to what? 7.5 kilonewton meter here. Then, if you wanted to show M over EI, you must divide it is 7.5 by, if it is a steel beam, 7.5 times 10 to power 3 Newton meter divided by 200 times to power 9 Newton per meter square times E times I. Assume that there is a value for I, for example, if it is an I-beam, I-180. 180 means this time to here, deep is 180 mm. This is 98 mm. This is 10 mm. This is 11.4 mm. Then I is 7565, 10 to power minus 6 meter power 4. Then put this value here, 70.6, 10 to power minus 6 meter 4. This is why you divided the value of the moment per IE, modulus of elasticity, and I, second moment of area of the cross section of the beam. Assume an I beam here, which is called the nominal size 180. But this is not 180 actually. This is nominal size. The exact size is 178 mm. But this is called S 180 times 30 IV. What does it mean? A standard designation. 180 is the nominal size depth of the beam. In the market, they know it as a 180 beam. 30 means each meter of length of this beam, the weight is 30 kg, kilogram. Okay? This is anything about the deviation, deflection, slope.